tool, so hopefully the screen doesn't go out, but I make no promises. I have backup ready. But recapping Tuesday, then we got into, okay, in chapter 6, we have the z-test, but to do the z-test, we need to know the standard deviation of the population. And if we don't really know a lot of information about the population as a whole, can be hard to know that information about the standard deviation of the population. So what can we do? We can estimate using the sample's standard deviation. And when we estimate with the sample standard deviation, this is called a t-distribution. And because the sample standard deviation has some error to it, because we're just taking a bunch of samples to get our sample distribution, there's more error than the precision of knowing the population has this much spread. We're looking at a small sample of the population has this much spread. So there's some more error put into it. With that more error, we get more area in the tail, so it has a slightly different shape than the normal distribution, known as the t-distribution. And so ultimately it came down to the process remains the same, except now we need to work in the degrees of freedom. How do we find degrees of freedom in general?
1, 10.
Backwards. And -1 degrees of freedom. And -1. And so then that gives us what populations we can look at, and we got the various pieces for constructing the confidence interval remains largely the same, except now you're using the sample's standard deviation and T star based on the degrees of freedom, which we can look up in table D. And then running a test, again, remains largely the same, except now when we look up our information, we have a t-score now, and we're going to find our p-value using either table D, and we saw table D does not have as much information on it as table A did, so finding the exact p-value from table A doesn't really happen. We more find an interval that the p-value would be in by finding, here's where my t-score would land. So here's where the p-value would be between. Or I also showed how we can do it with a calculator. And then right at the end, we got into 7.2, which talked about, once again, not always the most realistic to look at one mean. What's more realistic is looking at two means. So more typically, we're going to look at a difference in means of two populations. I can find our note for today. So more typically, we're going to ask that question, how different are the populations? And with that question, our parameter of interest, H naught, the thing we're going to look at for H naught is mu1 minus mu2. And then when our data comes from two samples, our best guess for x1 minus x1 bar minus x2 bar is mu1 minus mu2. And when those samples are actually independent, the true standard deviation by standard deviation rules would be this long thing where it's the variance of our first population over the sample size with the variance of the second population over the second sample size square root of all of it to get the standard deviation. We don't know the standard deviations of the population. That's where our t-test is coming in. So we estimate it with the sample of the standard error is going to be the same thing, but replace out the sample standard deviations, not the population standard deviation. So this is population standard deviations. We are replacing them with the sample standard deviations. And so it pulls back to chapter 1, where if we're just given data, we're going to need to find the standard deviations. And there are the steps in the calculator to do so. And so we got, as normal, our test statistic is estimate minus parameter over standard error. The estimate being x1 bar minus x2 bar. The parameter being how different are the means. Typically we don't want a difference in the means, or we're trying to see if there's a difference in the mean. Meaning our parameter is that there is no difference in the means. So we plug in 0 for our parameter. And then the standard error is that long formula of the square root S1 squared over N1 plus S2 squared over N2. And so we have our t statistic to calculate. And so we get our t statistic. We can use technology or the book telling us what the degrees of freedom are. Being told what degrees of freedom are. I said this is anytime you see a k equals, that is telling you what the degrees of freedom are. Or if we don't have that information, we can use a conservative approach. That is just the smaller of the two degrees of freedom, the smaller of sample size minus 1 between our two samples. So we got a high school wants to compare two methods for teaching Algebra 1. This is where we left off. Method 1 is a new interactive problem-based curriculum. Method 2 is the traditional lecture-based curriculum. 42 students randomly assigned. So we're told it's random. To 2 methods for a semester. At the end of the semesters, all students take the same test, and the results we get are that method 1, we have 20 students assigned to that curriculum. Their mean score was 78. Their standard deviation was 8. Method 2 had 22 students assigned to it. Their standard score was 73. And their standard deviation of their sample was 10. If we're just looking at these 2 samples and thinking of our samples as the population, yes, method 1 students scored better. But we're trying to give evidence for they scored differently enough to try and put method 1 in place. So we're trying to find, is there convincing enough evidence that method 1 will continue to give us higher scores, and so we can convince the teachers at the school to put method 1 in place in all those classrooms. So our hypothesis was H naught being mu1 minus mu2 is 0. We're trying to test if method 1 is better, if method 1 is bigger, if method 1 produces higher exam averages. So our alternative is one-sided, and particularly that difference is greater than 0. We also got the degrees of freedom. We're going to use the conservative approach here, where it's the smaller of the sample size is -1. So in this case, that was 19. And so we need to find our t-score and then get the value for that. So to find our t-score, first thing we would need is that standard error. When I'm referring to the standard error, that's the big square root. It's the square root of S1 squared over N1, S2 squared over N2, and these are all pieces that were given. What is S1? And what is N1? 20. So we'd have 8 squared over 20 plus, similarly, 10 squared over 22. Square root of all of that. And can somebody with a calculator calculate out what that gives us?
$2.78.
2.78. This is that denominator portion of our t-score. So then with our t-score, in the two sample, we're taking the difference, x1 minus x2, over that big square root. So that's our mean scores. That's filling that in, minus x2 over the big square root. X1 bar minus x2 bar would be 78 minus 73, all over 2.78. And trying to pull up calculator stuff myself. To work through this. What, first of all, does that simplify down to?
Like basically 1.8.
1.8. Essentially, you should be getting about 1.8 on that. Doesn't matter. Come on. Give me the end matter. Thank you. Okay. And so I showed on, okay, we'll go here. We saw how to find this in the calculator. So 1.8 is our t-score. So in the calculator, we can get the precise p-value. That was the most random ad of just a very AI picture of a bunny. Okay, second distribution. We are doing T, so we'd have TCDF. We are going from, since we want bigger stuff, our lower is that T score, and we're going up to the infinity. E99, 1E99. What were the degrees of freedom? 19. And paste. We get 0.0438. So, since this is one-sided, that is our p-value. We don't have to worry about doubling it. Our p-value from technology is 0.0438. Is that bigger or smaller than our typical significance level? Smaller. What is the typical significance level? 0.05. This is smaller than 0.05, our typical significance level. And so when we're smaller than our significance level, what does that tell us to do to our null hypothesis?
Reject it.
Reject. We reject the null hypothesis. Rejecting the null hypothesis means we conclude the alternative is true. The alternative, mu1 minus mu2 is bigger than 0. What is that telling us about the two methods?
There is a difference.
There is a difference in the two methods. Specifically, there's a way that the two methods tend to lean. Which one's better?
Method 1.
Yeah. Since our null hypothesis was that one-sided, we're seeing the one that's bigger or is the better. So method 1 is a better method. Method 1 produces higher test scores. All right. There's a whole bunch of room there if I had run out. So method 1 produces higher test scores. Beyond this, we have our test for significance. The other thing we can continue to do with our data is we can continue to have confidence intervals. And the confidence interval is largely set up the same. Estimate plus or minus margin of error. Margin of error being T star, based on our degrees of freedom, times that big square root. So when we have the 2 sample, we have the big square root. So when the random, normal, and independent conditions are met for a level C confidence interval for the difference in the two population means is that big formula. T star is that critical value that we can find from table D. And we have our degree, using our degrees of freedom. So look at an example of this. An educator believes that new directed reading activities in the classroom will help elementary school pupils improve some aspects of their reading ability. The educator arranges for a third grade class of 21 students to take part in these activities for an 8-week period. A control classroom of 23 third graders follows the same curriculum without the activities. At the end of the 8 weeks, all students are given a test which measures their the aspects of their reading ability that the treatment is designed to improve. We have a bunch of data here. The difference now with the bunch of data is we actually need to find the mean and standard deviation of both the treatment group and the control group. So I'm going to call them XT and XC. Or X bar T and X bar C. And then we'd also need the standard, wrong standard deviation. We'd also need ST, the standard deviation of our treatment group, and the standard deviation of our control group. So with a calculator, again, I'm going to try and just do the treatment. We can put all the data in, because for the mean, yes, we can add them all up and divide by 21. I think is this one. So we can add them all up, but to find the standard deviation, it's faster to type them into the table. So stat edit. Wish I was working with a regular calculator. So much faster. Put the treatment in, assuming I didn't make any typos. And then we can calculate our one variable stats from that. So stat calc one variable stats. And it gives us all the different pieces. And we have the mean is 51.47, that top one. Or sorry, 0.58. And then remember back from chapter 1, it gives us two different standard deviations. Which one do we care about? The capital S or the sigma? Which of those is
S.
capital S? Why? Which one?
Sample.
It's the sample. Capital S is our sample. This is if this was the whole population. That's the population standard deviation. Technically, we don't have more people, but there was a thing we talked about, I think, in chapter 5 of our population as a whole is all third graders. We don't know the standard deviation of all third graders. We just know the standard deviation of our little sample of third graders in the treatment group. So that was that difference. Sample versus population. I said we're going to use the sample one. And here is why. We are looking at samples. most precisely in this class. So. So that information is, it's up. I just need to make it bigger. The mean we got there, the X bar was 51.48. The capital ST was 11.01. And we could repeat this for the control group. Calculator could give us the control group. I have the numbers. You should get 41.52 for X bar if you put them all in and found their average. And you should get 17.15 for the control standard deviation. So there's our pieces. We want to test if there's a difference between these. So we are trying to test if the mean of the treatment group minus the mean of the control group has a difference. And sorry, backing up, we're in the confidence interval part. So we're trying to find an interval representing the difference in the scores. So our goal is to estimate the difference between the two scores at a 95% confidence level. So that down here gives a check conditions. There are 3 conditions that come with the t-test that we generally have to check. For the most part, it's a make sure there's not large skewedness. So we check that it's normal, not large skewedness. We check that it's random. Checking that one, we'll come back to actually check normal, but checking that one, this is about as random as it can be. They used pre-existing classes, but one, I don't know if it necessarily states it, but they're essentially using classes with the same reading teacher then. So the teacher isn't adding any variability or lurking variable. And they were probably randomized to a degree at the beginning of the school year when they were assigned to their 3rd grade classes. So they're as random as they can be, but they're not going to mix up students mid-school year. Just for a random aspect. They just used existing classes, but on average, these were very similar classes. Used existing. But those classes had been randomized as much as possible in that real world using existing classes setting. And then independent, there's not students overlapping. One student, one class is not affecting the other class. So independent as well, the 2 groups are independent of each other. and independent. Yes, groups are independent of each other. Now, on Tuesday, to check normal, one looked at numbers when it was really close together. There was I think a diameter of some part problem where we just checked, hey, these don't look like it has any big outliers. They're gonna be pretty much clumped together. In a one where we weren't able to tell quite so much by looking at the numbers, I made a stem and leaf plot. So we can make a stem and leaf plot for that checking of normality. And another way we can check normality is looking at the normal quantile plot, which for the most part, I think I've only shown in class, but on that calculator thing, there was a, how do we find the normal quantile? How do we find it with our calculator? We can find that normal quantile plot by going to second stat plot and going to plot one, enter. I'm going to turn it on. And in this type list, we have scatter plot. I believe this is scatter plot with the points connected. Histogram, box and whisker, two types of it. And then this last one is the normal quantile. So you can get a TI to do the normal quantile plot, which basically finds the z-scores of every point and then plots them. And if we do that, we want to see basically a straight line. If it's normal, we'll get a straight line. If it's not normal, we'll see some curvature. So I'm trying to select that. And then it changes our information. We want the data list to be L1. Typically, what we view more, at least what we see more in this class, is for the data axis to be Y. So I'm going to change that. But in general, if we have, no matter which way we do it, we want to see a straight line. So then second, nope, not second. Zoom stat, zoom 9. And there is our normal quantile plot. It's not perfectly straight, but for the most part, again, the idea we don't want large skewedness. We don't want large outliers. There's nothing jumping out as, oh, that point there is really bad for us. We mostly have that straight line. We mostly have normality. We have at least enough normality to use this. And we could check the other one as well, but they are both mostly normal. So look at standard. Looking at the normal quantile plot, we see, yeah, these are both mostly normal. There's no large skewedness or outliers.
What did we hit to plot it again?
Zoom 9. That is zoom stat. Yep. Mostly normal. The quantile plot, the normal quantile plot, showed a straight line. More mostly straight line.
Data access was which one again?
I used Y.
Okay. Was there a reason for that?
That's the one that we see the most in
Okay.
when we're given them in this class. Because they do show up throughout the book, and it always puts it on that axis. But if we're looking for a straight line, it doesn't matter if it's on the y-axis or the x-axis. A straight line is going to be a straight line. All right, so conditions checked. Our data is mostly normal for our two groups, mostly random as much as we can, and the two groups are independent of each other. Great. So now we can actually continue with our goal of creating that 95% confidence interval. x1 bar minus x2 bar plus or minus t star square root s1 squared over n1 plus s2 squared over n2. At this point, it's fill in information. Generally, there's still one more thing we need to find. But x1 bar and x2 bar, we know. S1 squared and s2 squared, we know. That's our TC. TC, we know those as well, 21 and 23. The only thing we don't know yet is that T star. So we can look up T star on our table D. So we went through that on Tuesday. Macmillan, I had the ebook up. Here we are. Table D.
Where did it say to use a 95% confidence?
It
We just assume.
that was the problem we were gonna do. So it didn't actually say it, but I put it in as our goal. That's what we're gonna do.
Okay.
It didn't actually say it. I put it in there as this is our goal. We're gonna use a 95% because we're talking about the confidence interval here. Problems will be more clear than just here's some data, do something with it. So our two treatment group sizes were 21 and 23. If we are just assuming a degrees of freedom from that and not using technology to get one or using a book to get one. If our two sample sizes are 21 and 23, what would be the degrees of freedom? Conservatively. 20, the smaller minus 1. So 21 minus 1 is 20. So we're going to look in this 20 row, the bottom of this blue section. We're doing a 95% confidence interval. So what would the upper tail size be? Basically, which column am I looking in? So we would think that, but if we take a curve, where did all the chalk go? If we take our curve, our 95% confidence interval is centered. So we are splitting that, and I said, the table says it's the upper tail probability. So we just want what is left in there. 0.025, yes. So we're going to look down our 0.025 column until we reach 20. I'm going to at least put my mouse on that 0.025, go down to 20. And that gives us a T star of 2.086. If we forget how to read this, there are two ways to read this table. We can also go all the way down to the bottom, and it gives us our confidence interval size on the bottom. So that column lines up. The bottom of it gives us the 95%. The top of us gives us that 5% divided by 2. So reads it both ways. Interesting. That's not a table I want to look at. There we go. Okay, so it was 0.2086 or 2.086 as T star. The square root, I was about to be like, oh, we've calculated this. No, we calculated it for different numbers. Square root of 11.01 squared over 21. There's our ST. Plus 17.15 squared over 23. That's our SC. And then XT minus XC is 52.48, 51.48 minus 41.52. Somebody, what is the 51.48 minus 41.52?
9.96.
9.96. What does this one simplify down to?
8.98.
8.98. So we estimate there's a difference of 9.91 points. I don't think it told us if it was out of 100 or not. Plus or minus this 8.98. I have it rounded to 99. Not that that's terribly important. Because I'm still now questioning the math here. 9.96 minus 8.99 is what? 9.96 minus 8.99?
0.973.
0.993.
973.
Oh, 973. 973. And then 9.96 plus 8.99.
18.95.
So the difference in the scores is between 0.973 and 18.95. There would be a sentence of the difference in the scores for the two classes can be estimated with 95% confidence to be between 0.973 and 18.95. Our typical null hypothesis for a two mean test is that the means are the same, or the difference in the means is 0. Is 0 inside this interval?
No.
No. It stretches from about 1 point up to 19 points. It does not contain 0, meaning if we were to run a hypothesis test, we would find that there is a difference in the scores. In particular, the treatment group is scoring higher by an amount of somewhere between 1 point and 19 points. So the treatment group is scoring higher by 1 to 19 points. Just boxing that off just so things are starting to run together. So we know our treatment group, if we were to run a hypothesis test and a t-test, we would get that the treatment group, that there is a difference. The treatment group is scoring better. So here, this probably should have fell earlier. Here is our two sample t-test definition. It's what we already used when we did our example on the algebra one, where there was the activity-based versus lecture-based. and the activity base scored higher. This is ultimately what we were using when we test our null hypothesis. It's the same information, grand scheme, as all our other tests of we find a t statistic in this case, plug the information in. If we are one-sided, we are either finding that t, the probability of the upper tail, the probability of the lower tail, those are just the p-value, or we need to double that probability for a two-sided. So it's that same idea of on a one-sided test, we just find our probability, that is our p-value. For a two-sided, we double it to get our two sides. So let's actually run that for our directed rating activities, the example we just did. We're going to do it again, but this time instead of the confidence interval, we're going to run a two-sample t-test. We are testing the null hypothesis. I'm going to replace it with our t and c. We're testing mt minus mu c is 0 against the alternative, the treatment scores higher. So that just matches the T and C, so we know which one's the treatment versus the control from before. Running our test, we need a T statistic. We've already checked the conditions. We've already checked that this is independent, normal, and random. So we need our T statistic. Our T statistic is xt bar minus xc bar all over the square root of st squared nt plus sc squared over nc. Just replacing ones and twos with t's and c's. But we've actually found all of these numbers before. Actually, scratch that. We found this multiplied by 2.86. We multiplied that one by t star. So we need to refine that without t star.
4.308.
Thank you. So we should have gotten, if we plug them in, let me write them plugged in real fast, just so we see where we're coming from. This was 51.48 minus 41.52 all over the square root of 11.01 squared over 21 plus 17.15 squared over 23. And so this top part we know is 9.96 from our confidence interval. We already did that subtraction. And Matt, what did you say the square root one was?
4.308.
4.308. 9.96 divided by 4.308. Me with a calculator.
2.312.
2.312. Conservative degrees of freedom was 20. And I want to re-talk through the non-technology based way of finding a p-value. We go to that degrees of freedom row, 20, and we find where 2.312 would fall. 2.312 in row 20. I'm trying to make that bigger. So 20 is the bottom of blue. 2.312. If I ever mix that up, please correct me. 2.312 would be between this 2.197 and 2.528. 2.197 and 2.528. So 2.312 is between 2.538, 28, and 2.197. Since this is one-sided, if I go to the top of the column where this is, that will be our p-value. In particular, this is the probability that t is bigger than 2.312 is what we'd be told at the top of the column. Again, because this is one-sided, that is our p-value. So I'm going to look at those two columns. Here they are. I'll put my mouse between them and scroll up to the top. That probability is between 0.01 and 0.02. 0.01 and 0.02 was where that fell. We don't know from this method exactly what the p-value is. All we know is it falls somewhere between those two numbers. But anything between those two numbers is still on the same side of alpha, of 0.05. Are 0.02 and 0.01 bigger or smaller than 0.05? How do these compare to alpha? Particularly, let's look at the bigger one. How does 0.02 compare to alpha? It's smaller. And 0.01 is also smaller than alpha, meaning our p-value is smaller than alpha. P-value smaller than alpha tells us what about our null hypothesis?
Reject it.
We reject it. We reject the null hypothesis. There is a difference. And in particular, that difference is that our treatment group is scoring better than our control group. So we reject the null hypothesis. Specifically the treatment group scores better than the control. And once again, that is exactly what the confidence interval was telling us. Treatment group is scoring higher by 1 to 19 points. So the confidence interval gives us a little bit of how much better are they scoring? Treatment group could be scoring as little as 1 point better, which is still important. I'd love scores to improve by 1 point, but I'd much prefer them to improve by 19 if I was teaching these sections. But the null hypothesis, or rejecting the null hypothesis, tells us there is a statistical significance. The confidence interval kind of helps us to determine if that's practically significant or not. Because we would reject the null hypothesis even if this was as low as 0.001. As long as this one was bigger than 0, we're getting that reject the null hypothesis. All right, so some rules. These are very much the same ones from 7.1, except in the case of small samples, we can, as long as we are from a random sample and that they are independent, that is more important than being normal. So that's where that normality is kind of hand wavy. It's important, but we just really want, there's not a lot of skewedness and there's not a lot of outliers. So if we have the two samples together is less than 15, we can use it as long as there's not a lot of skewedness and a lot of outliers. If there is a clear skewed property to this, we can't use the T procedures. If we have at least 15, we don't want the outliers, but we can generally proceed with caution for small outliers and small skewedness. If it's very strongly skewed, again, we can't really use it, but we're just looking for skewedness with that normality. And then large samples, we're free to go because of the central limit theorem and that we're getting closer and closer to a normal curve. The larger and larger our samples get, we're getting much more likely to be able to use them. So as long as our samples are large, use T procedures as normal. All right. 7.3 gives us a little bit of sample size items. And so before collecting data, we should be before collecting data, we need to be checking. We should be asking how big of a sample do we need to collect? To get the precision we need of how much of a margin of error do we want. So our precision ultimately is controlled by our sample size and the standard deviation of our samples, our standard error. And so our primary method when choosing a sample size, the thing we can control the most is our sample size. We would specify how big we want our margin of error to be. In particular, this is the same idea from before, where our margin of error is that T star S over square root N. Or the more complicated in the two, but T star S over square root N. And so we can control this margin of error by the sample size. So if I wanted to solve for, I'm just going to call it M for margin of error. If I wanted to solve for N, if I wanted to solve for the sample size, how would I solve for the sample size? How do I get N by itself? Yeah.
You take m sorry, the square of um m divided by t um then
Yeah, I think you're getting there. Kind of looking for the steps in between, just so we know we get it right. The algebra steps in between of getting this N here by itself.
multiply both sides with square root.
Yeah, square root N is T star S over M. Square it. So breaking it down, we make sure we're getting it right. Definitely heard right things. And so there's ultimately a strategy for the T procedures. We get an initial sample size by using Z star instead of T star. We round up and then we check it with T star, M greater than T star, S star over square root M. We check it, make sure that margin of error is appropriate. If that requirement is not appropriate, we increase by 1 and repeat. Otherwise, we stop. Looking at things and looking at time, I actually want to switch off of this and we'll finish this in a week. But I want to look at an example or give you guys time to work an example of the two-sided, because finding sample size, we've talked about this before a little bit. It changes a little bit with T star, but not enough. We'll come back and finish out these notes in a week. But I want to give you guys a practice problem right now. So this is going back to just the two procedure. So the practice problem where I want you guys to find the confidence interval and the test a hypothesis. With this information. Take one, pass them back. There are definitely enough for everyone. So if I didn't give enough in a row, check the other rows. So trying these problems, asking questions, try and work through them. But I want you guys to try them first. Feel free to work together, check with each other. Oh, I didn't save it. I need a blank document. will say, working this real fast, there are two different degrees of freedom that could be used. The conservative degrees of freedom, what would be the standard one that we could do just based on sample sizes? 10. I'm assuming the squirrels have, the espresso squirrels have 11 in it. So that would be 10. I also have calculated the tech one of if the book gave it, it would say K equals 15.2. So you're welcome to work with either of those as your degrees of freedom. But there are two different ones.
Dr. Mays,
Hmm.
I count 10 items for the espresso school.
Oh, so is it 9?
Yeah.
Okay, I have not actually counted them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So conservative would be 9. Yes. The smaller sample size was 10. So 10 minus 1 is 9. Welcome to work with either one of those while you're doing this. All right, looking at a little bit of it as we start. What were the mean and standard deviation for the espresso squirrels? Let me get those.
18.36.
18.36 for the mean and standard deviation. 1.0, what, 3? As the last decimal around that. Okay. My calculations could also be wrong, so. Okay, so then with our 95% confidence interval, how do we set that up? Basically, like, what would be our formula?
The difference in means plus or minus T star.
Yeah, I'm gonna use XE for espresso. And what are they? Normal? Regular? Plus or minus, what were you saying then? T star? And I'll just say big square root. It's not the most fun to quote off. Plus S R squared over NR. And filling those in, what I only have the espresso in front of me. 18.36. What is the regular squirrels mean? 0.1 plus or minus T star.
1.833.
Which degrees of freedom did you use?
9.
9? Okay. 1.833. Did anyone do it with the 15.2? No? Okay. That's okay. 10 plus 2.5 squared over 12. And what do the two different things simplify down to of blank plus or minus?
Negative 1.74.
Negative 1.74. Plus or minus
1.45.
1.45. All right. And so negative 1.74 plus 1.45.
Minus 0.289.
0.289. And then negative 1.74 minus 1.47.
Minus 3.19.
Okay, there's our confidence interval. So the espresso squirrels being first, the fact the subtraction is giving us a negative number. In this case, all of our other examples, we were talking about like scores. And so one being better than the other would give us a positive number. But in this case, we're talking about times for running a course. We want a faster time. Faster would mean a smaller number. So we have smaller number minus bigger number giving us these negatives. So the espresso squirrels are running faster, somewhere between negative 3.19 seconds to negative 0.2089 seconds. So we are 95 are 95% confident are espresso squirrels. Again, to actually say it out loud verbally, don't do this. Don't give squirrels espresso. We are 95% confident the squirrels, espresso squirrels. I started the word squirrels already. Complete the course. .19 to .289 seconds faster than the regular squirrels. Quickly talking the other, just wanted to get null hypothesis and alternative. The null is that they are the same. They run it in the same amount of time. This case, the espresso squirrels being faster. That is the idea we have to think through. Faster means smaller number. Smaller number minus bigger number. Will that be smaller or bigger than 0? Smaller. So this would be our alternative. And I'll just ask, what p-value do we get? If anyone got that. My knowledge, but I think some of these numbers might have been calculated wrong. Numbers it should be around 0.02. Somewhere in there. I encourage you guys to check that and try that, but we're mostly out of time. But either way, what we should get is reject the null hypothesis, meaning the espresso squirrels complete the course faster. All right. Do I still have announcements up? I don't think I do. Yeah, I don't have announcements up anymore. Remember, you have a post-class activity due today. Your next one, the one that is technically assigned today, but has been opened since Monday. The one that's technically assigned today is due in a week because we don't have class until a week from today. So we'll see you all then. If you have any questions, let me know. Have a great couple of days. See you in a week or possibly before then, somewhere around Focus Series.
Yeah, thank you everyone. Yeah.